Okay, so we are going to see week 10 content there. Uh, you know, we, we'll see the KKT conditions, and also there are some applications of whatever we learn in convex set and convex function we'll use, which is we'll say it is already, you have seen the gradient, sorry, linear regression. So you will see that one application also of the optimization. And yeah, so KKT, sorry, so convex functions properties are there. Then there is one use of them, and the third is the KKT conditions. Okay, so let's start this. Let me present my screen. Just a minute. Okay, so let me present my screen. Okay, so in week 10, is that there are some property of the convex function. Okay, so last time we have seen, a convex function is what is a convex function? Convex function is a function which have if you see the epigraph of the function, that is a convex set. And what is a convex set? Convex set is a set which, if you do the linearization between 2 points, it will be lie within the set. This is the rough definition we have seen even, and more concise definition already in the lecture. So these are the things first we see in the convex set, and then we have seen the convex function. There is a equality condition also, you can say, that for the concave function. Concave function is if the function is if you say it, the minus of If you see the minus of, if you have function fx, if you do the minus of it, that is a convex, then we can say the fx is a concave. So reversible form. We have seen the same thing we can apply for the concave also, but the condition is if we do the minus of it, that will be a convex. So if you want to check fx to be a, let me change the color here. So you want to change, if you have a function fx, you want to check is this a concave or not, no? So what we do, just check that minus of fx is a convex or not. So my screen is visible to all of you?
Yes, sir.
Okay.
Yes, sir.
Okay. So this is what we have seen in the convex function. So we have seen the different definitions also for the concave. When we sorry, convex, when it will be the convex, we have seen the 4 definition. There is one for the multivariable, we have seen the Hessian, and if it is not multivariable, if it is in one variable, so simple definition is that we have that fx, you know, so less than or equal to, so lambda time fx plus 1 minus lambda time f of x. So these are some, we will say if the function satisfying this condition, then we'll say this function is a convex function. And some of other definition there regarding to the epigraph, Hessian, and one more definition I think is there. Okay, so these are some definition for the convex. Next is we till now didn't see, so we have seen one use of this, that if your function is, you know, convex, then you know the local minima is become global minima. That is what the another property, and the proof of it is given by professor very nicely. Arun sir is explaining that how it will be a local minima would be a global minima. So this is what they are related to the function, but there could be some condition when sometimes we not able to recognize the function is a convex or not. Sometimes it would be difficult also. So in that case, we can think our function with the 2 separate functions. So I mainly want to focus on 2 properties here. When a function would be, you know, 3 properties is there, I think. One is when we add 2 functions, then it will be convex or not. And the second thing is that when we are taking the composition, and there are 2 separate things. One is the for the non-decreasing case, and one is the linear case. The 2 different, there are 2 different composition or composite function with the 2 different condition. Okay. In that case, we'll see when it will be a convex or not. Okay. So sometimes, you know, I mean to say sometimes your function is very complicated, let's say of this case. It's look like a bit, not very complicated, it's look like complicated expression, but you can break your problem into different functions. So like, you know, when we used to draw our function in the, you know, in, if you remember in the J advanced problem, those some, or maybe you want to graph a function. So first, you know, how you used to see, even if you studied, you know, polynomial. So there you used to see that if you have a polynomial, then just break or see the coefficient, and slowly what is going to be in upward, lower direction, sorry, in upward direction or lower and downward direction, when it will be touches to minus infinity, when it touches to positive infinity, by looking the, you know, by looking the uh, coefficient we used to say. So what is that? We used to break our problem in the coefficient kind of thing, and then so similarly here, when our function is a bit complex, in that case we break our problem or break our function into different, or maybe is this function is a addition of 2 function, or is this function is composition of 2 function. Okay. And once we got that, okay, is this a composition of 2 functions? So let's check that the condition that, okay, both are separately convex or not, one of them is increasing or decreasing or not, or one of them is linear or not. So using this property, so these properties are actually useful to check that your function is convex or not. Okay. So the first condition is the related to the adding of two convex function. Okay, so if you have the first property, if you see here, that if you have two function fx and gx, and if you add them, so will this be a convex or not? The addition would be well defined. Okay, so the it will be a convex or not. It's depend on if both functions are convex. If both functions are convex, then their addition is a convex function. So and the addition, how the addition is defined, it should be, it should be given. It will be given, or it will be well known that this is a simple addition. Simple addition in the case of, let's say I have a function fx is equal to x square and gx is equal to x to the power 4. Okay. So if you think a function hx, okay, of this case, so see, it's look like a bit, now you have two added function, two variables, or sorry, two functions here generally. Two functions added here. So see, it's look like a bit complicated, but if you break your problem, it will be more easier. Now see, this is a convex, we know already, and x power 4 is also, if you want to see the graph, it can easily, by graph you can see this x square is like this, and x to the power 4 is more like this. The gap would be less. And separately, if you see, both are the AP graph is a convex set, so both functions are convex function. Now both are convex, so separately, sorry, both compounds separately convex. So addition is going to be a convex function. So see, the addition means you are just adding the variables, particularly as it is defined the per term also. Sometimes the addition would be differently defined also. Okay, so it's depend on how the addition is defined. You are doing here a simple maths, not so deep. Otherwise in mathematics, defining the addition is a very different way to you can define the addition of two functions. So here is a simple addition as usual, So by this way you can say if two function is convex, their addition is going to be a convex function. Okay. Is this clear?
Yes, sir.
Okay. Okay. The next property is related to the, see, so this is what I want to say. The f is a differentiable convex function from D to R, then as a global minima of f if only if. So that is saying to be, already checking the critical point. See, this is the in the thumbnail, the theorem it's here. So what is this theorem? If the function is a differentiable convex function, okay, this is for any general function. Okay, see that the function is from Rd to R, a scalar function. It is called a scalar function. From the vector, from the vector, the function is from vector to a scalar. The map is, or you can say a multivariable function. So this is a multivariable function. Okay, and it have the global minima of f if only if it have just an x star is said to be a global minima. So here just need to see it if it is a, if x star is saying to which is from Rd. Okay, we can say this is a, so let me write the full theorem here on that and with explaining it. So what the professor is saying that we have a function f, okay, which is from Rd to R. Okay, so what it means that it is saying to be a multivariable function. It means that you have a f of x, y, z, or any of w. I am taking the 4 dimensional. So this is a vector in R4. Okay, to R. So this is to R only. It means that this is a, you will get a real output, or generally it is called a scalar function also. So you can say this is x square plus y square plus z square plus w square. Okay, this is a kind of function. The notation is telling you this one. Okay, So if you have this function, then the condition is needed if it is a differentiable. Okay. The generally in this course, whatever the function would be given, you no need to check is this differentiable or not. It's properly said that okay, is this differentiable or not. Okay. Otherwise, in multivariable, there are more condition to check the function is differentiable or not. You have seen in maths too, very small lecture, but it's needed more. Okay, more information. So generally, it would be given a differential function for you. Okay, so function is differentiable, and the next is it should be a convex. So it's very easy to see it. This is a convex function because you know this is if you do the if you check with the Hessian matrix, you can easily get this is a convex. Or if you say if you try to visualize, we cannot visualize as for, but if you remove this one. So if you try to visualize this at least in 3 variable, it will be of this case. So no, even this is needed to graph it. It needs just 5 dimension. Okay, we have to at least remove one more. Then so if you think of this function, this is going to be of this. So the EP graph, it's if the EP graph this function is going to be a convex set. So even if you're increasing with the same pattern, it will be a convex. By EP graph you can check, or by uh, uh, the way the Hessian. By Hessian is a simple method you can apply to check it. So this is a convex and differentiable function. This is a polynomial. This is called polynomial in multivariable. Okay. So we'll say so suppose I have this function. So we'll say x star, okay, which is in R4. This is a function in R4. We'll say this is a global minima. We'll say this x star is a global minima. So if you want to say x star global minima, so it's needed if you find the gradient, it should be equal to 0 at s star. If the gradient at the critical point, gradient in 0, will call it as a global minima. Otherwise, if you have a global minima at particular point, then the gradient at that point is 0. Already. Many times you are doing the multivariate function maxima minima. How you used to do in the maxima minima? You used to find the first gradient of it equal to 0, and then using that you used to find the critical point, which is x star. And by that way you see that your matrix is positive definite, or there are so many things, or if in the 2 variable we know, or till in maths 2 we see in the 3 variable, the Hessian case, this should be positive, this should be positive, and determinant should be positive, then it is a what is that? It is a local minima, right? Anyone have remember the global minima, local minima condition, at least in for the 3 variable?
Yes, sir.
In the form of Hessian, right? So simply, if it is a positive definite, then it is a global minima. If it is a negative definite, it's a global maxima. In that a different word is there, you can recall from there. Okay, it is not tough. Simple conditions are there. Just recall it. If you just do the Google search, you'll get okay in the Hessian form how we can get that a function have the global minima. Or best thing is we just recall yourself. That would be good. Okay. So this is what it's saying. Our simple method to find that. So it's mainly this theorem says that if you have a local minima, that is your global minima. This theorem tells you. Okay. So the first property we have seen now. This is the theorem we have just now discussed. Now the next property is that we call our function. Now we are going to see it in the. So again, this composition will help you to break your problem in the simpler form. Sometimes your functions look like very complex. Okay? So you can break your problem in the simpler form. So this is for addition, and the case is needed for 2 condition is needed for composition 1. So the case is that, so there's the second property we can say. We suppose we have a function fx, okay, which is convex, okay, which is convex, and gx. So this gx is also, let's say this is a convex. Okay, so if both functions are convex, okay, and if you do the composition, okay, this is not necessary your function is convex. Okay, composition may not be convex. If both function even convex, your composition may not be convex. But if we impose one more condition, okay, what is the condition? I am imposing the condition on f. Okay, the condition of is non-decreasing. Non-decreasing. See, I am adding the non-decreasing. Many people have that. What is the meaning of non-decreasing? So what is a non-decreasing? Non-decreasing, you know. No? Decreasing means continuously decreasing. Non-decreasing means this case. So decreasing, you know, if you have, suppose you have a graph, so the graph of the function is slightly like this. So this means that your function is decreasing. Your output is continuously decreasing as the input is increasing. This is called decreasing function. But non-decreasing means you have decreased, okay, sometime, but at some time the value is same. You know, some fix is there, and then again it started decreasing. But at particular point, maybe within some range, sorry, within some domain, the value is fixed, and then again it's decreasing. Mean to say, sometimes your function have some equal values, okay, and lesser values. So non-decreasing case, yeah, if your function is f, okay, we'll say the non-decreasing if f of x1 less than or equal to f of x2. And strictly less than means, sorry, decreasing means strictly less than. You will not impose here. So this case you can say non-decreasing. Okay. So sometimes it's equal and then still lesser than. Okay. So this is the meaning of non-decreasing. So if you impose one more condition on f, okay, then your function composition is going to be a kind of. So then if you say here, it is going to be here. So it is not maybe, it surely says it is a convex. So two condition is needed. If you, I suppose I am reversing the case, what is going to be in this case? Z of your composition Z. So in this case, you cannot say, because you are not imposing the condition on G. Okay, we are only imposing the condition on F, and we are saying the convexity to this F compose C, not G compose F. Okay. So this is, be sure with, I'm not saying for this composition, I'm saying for this composition. Where imposing the extra condition, that would be the F will be the left side. This is what it is. If you want to see it example, so example is, let me create a function simply. Let's say of this function, let's say fx is equal to e power, so minus e power x, okay, and gx is equal to, let's say, x to the power o. Okay. So see, the composition is how very dangerous it will look like. So f of g, let's see that how it would be. So this is f of g of x. So see the f of f. So f is going to be our e power x. So still, yeah, it's looking simpler now. This is e power g of x minus is there. Right? This is how we generally used to calculate our composition, and g power x is minus e power x to the power 4. See, this is what it is. The JF compose C is there. So, not so complicated. Somebody want to say something?
So I have doubt in the non-decreasing function.
Mm-hmm.
Like we have I have remember like non-decreasing functions are functions they never will decrease. They can increase or
No,
constant.
no, 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 non. Sorry, sorry, just 1 minute.
Is it that or
Uh-huh. I think I just told the reverse layout just a second. So 1 minute.
that's why I asked.
Okay, okay, just a second. 1 minute. Ah, okay. Sorry, I told the reversible partner. Sorry, 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 sorry. I told you the sorry. Okay, so here is this is non-increasing. Sorry. Yeah. Thank you so much. Sorry, I just even in that mind. Sorry. So non-decreasing means, yeah. Sorry, this is a non-increasing case.
Sir,
So non-dec.
no, you were correcting. I mean, what actually should be non? I mean, is the definition of convex functions like that, or I didn't understand what is that part you corrected? Like
Mm-hmm.
you, okay, let me try to explain. You were saying that in the case of composition, uh, f and g are two functions, and if f is a non-decreasing function,
Mm-hmm.
uh, f of g of x. I mean, yeah.
So I'm not correcting on the definition. I'm just correcting the definition of. So I'm not correcting the whole theorem here. Okay. So I just missed that. Sorry for that. Yeah. Thanks for correcting me. So I'm not correcting the on the convex part. I'm just correcting here. What is a non-decreasing?
Ah, okay.
Okay.
Yeah.
So let me clearly. Sorry. Very sorry for this. This is non. I just told whatever. No. This is non-increasing. This is for non-increasing. So
One time,
you can say.
one thing more. Once you have written f of g may not be convex, and after that it's f of g is convex.
No, f of g is so that is a bit confusion. I said when you are not imposing the condition, you are just saying these two are convex. So yeah, if you are still confusion, let me know. If you are just saying f and g both convex, okay, sorry. So f and g both convex. In this case, the composition may not be convex. Here, in that case, may not be. Okay. If both function are convex, still it doesn't tell you that these two are convex. Okay. When I'm imposing one extra condition on fx that is non-decreasing, on f, then in that case your composition. So on the extra case, I separately wrote here. Let me write on the when on the extra case. Then f of g is going to be. Then composition is going to be convex.
So if f of x is decreasing or
No,
increasing?
non-decreasing, non-decreasing. So I
Non-decreasing.
told you non-decreasing. When extra condition when I'm imposing, both should be convex. Okay, and the next is when I am imposing one extra condition on the one extra condition on this f, then the composition is going to be uh, convex. Okay. So here,
So,
what I made a mistake. I made a mistake only on the definition of non-decreasing. Okay, this definition I told you for non-increasing. I made a mistake. Okay, this is my part mistake. Only I just everything is correct here. No error is there. The error is for the definition when we'll say a function is non-decreasing. Non-decreasing means it will never decrease. Means here it will be of this case. Either could be of f of x1 greater or equal to this is sorry. So in this case, I made a In this I made a wrong example given. I will correct it. So non-decreasing is this is what it is, or in a separate form. Yeah, I made it. No, so this is for non-increasing. So you can forget it. So this is I'm making wrong. So non-decreasing means this one. It will always be increasing, means of this case of this function. Either it would be increase, maybe sometime equal, but still increase, maybe sometime equal, and increase. A stepwise function of remember this type of function. This one, this one, this one. Sometime it could be increase and maybe equal. This is what the condition greater or equal to. This is the case. This is called non-increasing function. Okay. So here is I'm taking an example that your function is decreasing meant either it could be exactly increasing or maybe could be of this one. So I'm taking this function and I'm taking the composition. This is going to be so this is an increasing function. No? We know it. E power x is increasing function. Increasing function, and also e power x, if you see, e power x is a convex function. Not only increasing, it is both. E power x is this one.
What kind of
which is a
questions can be
convex.
asked week 10?
Sorry?
What kind of questions can be asked week 10?
From week 10 is this one. What I am discussing, the composition may be complicated. Some question would be given on the complicated functions, okay, to check that the function is a convex or not. And the second is on KKT. So KKT is be sure that KKT question related to the KKT concern so will be given. Okay. So is this clear? I just made a mistake, but I clearly specified that I just made a mistake on the definition of non-decreasing, but here the correct one is this one. Okay, and everything, the theorem is correct. Example I have given now, I have corrected it. A small modification is needed. Okay. Increasing function, and the x power is already convex. So here e power x is not only increasing, it is also convex function. Easily you can check with the epigraph. See, if you take the epigraph of it, that is a convex set. So this is a convex function, and the composition of both I am taking it, that is a convex. Okay. Thanks for correcting me. Is still doubt? Anyone wants to comment something? Or I made a mistake somewhere? I don't think now. It is fine. Okay. So next is the next theorem, the next property. Okay. The next property is when we take the composition with some, I will try to remove some condition. I will impose some condition on G. Okay. I will relieve condition on F. Okay. See what is this? So it says that when your one function is said to be linear, and the second one is given as a convex. So see the third property. The third property is now see here it is some relief is given between the condition. So one is a convex and second one is a linear, and then composition is taken, that is a convex. So what is to mean that? It means this one. So the third property is that I have a function which is a convex. This is just a convex. I have another function gs which is a linear. Okay. I have the first one is convex, the second one is linear, and now I am taking the composition. This is a convex. So composition is going to be convex. See the difference between the second condition, second property. The second property I am writing here f and g. It is this f is convex plus non-decreasing, and here is convex. Okay. So here see the differences now. It is not saying anything for the linearity of G. Okay. It is just said that, okay, it is not saying to be the convex. It is G said to be a linear function. And you know it in one variable case, linear functions are convex function, generally we say it. So, but no issues. So this is a function. Even we can replace of this function with the gx is as given as x plus c, or maybe gx is equal to, yeah, generally it is of in case. So this is a linear function. Linear function is a linear function which have the variable have at most degree 1, not at most, degree 1. A function where the variable contain only degree 1. That is your linear function. So this representing a linear function. Okay. And here is on f should be convex. And if I am taking the composition here, the composition is going to be convex.
In case of g of f,
So in case of g of c, it is not saying in case of g of c, now the composition is going to be totally different. So we cannot say anything. Okay. So still in this case may not be.
it would be a linear type something.
It could be a linear type, but it is not going to be in that, convex. So it is not giving the condition. Condition is when I am posing, you have to remember your proper composition, where how it is composed. Is this f of g or g of f? So this is on the some. These are some property of when we compose two function. So by this way, you can remember there is some relief now. This third property is giving some relief on the condition. Just saying to be f is convex, g is linear. So these three properties are important sometime to when you have a very complex function, you can break your problem in simple functions. And if you know that, okay, when you break your problem in simple functions, your problem simple function, you know the property of it, you can easily get it, or you can try it, able to try it, and then the composition, about the composition you can. So these are some property. The theorem is interesting. That is the you can use now that theorem. A professor is telling the use of the theorem in here the application. You can see when we have this properties, whatever we learn now, these properties now use, you can say, in the linear regression. What is the linear regression? So that the SSC you have seen, or linear regression is we have seen many times from the even the week one. From the week one we have looking the linear regression. This is just your function is a kind of linear. So let me show you that. So professor is not telling more, it is just saying that how it could be, how you can use or how you can apply these properties. So he's saying that why the linear function, sorry, what is the linear regression? He's not telling the linear regression, he's actually giving why this is giving a proper result. Is why it is giving. So he is saying that, okay, when we do the when we have h as a when we have a data, okay, and we apply the linear regression, okay, so our function is a kind of becoming or not becoming that when we finding the error of that function. So finding the error, the sum square error we used to find, and we want to minimize that sum square error. So a square function is convex, that is convex function, okay. And here is, you will see, if you see the proof, that is if you see this lecture, professor is using this property only, the third property, that the square function, when he is doing, let's say fx is there, okay, sorry, he is telling it as hx, okay. When you have hx of this case, okay, when you are doing the linear, you have some bunch of data. What is in the lecture? You have some bunch of data, okay, and now you are doing the linear regression of it, w transpose x plus b, when you are getting the linear, when you are finding hx, proper hx, or how you will find the proper hx, how you will get this w, okay, how will exactly you will get, we have seen the linear regression, okay. So while finding this w, okay, you have the data, this original data and the updated data, and then you used to find the error of it, like W transpose Tx plus P minus the original data. And that I think he wrote there, yeah, X, you see the notation. So this is going to be, a square of it, and then is norm it, something is there. So your square is a convex function. This is your convex function. Okay? And the inner part is a linear function. This is in your linear function, and here is the inner one is that the same will come here. So the inner one is a linear, and you are doing square. You are finding the square of it, and how it's happening now. See, you are taking the composition of convex and linear. So the whole composition is going to be convex. So by this way, where you find the local minima, okay, then this will be a global minima. Now the theorem is used in starting of the lecture, the first lecture. Local minima you found, and by this way, this is your global minima. And this is what the application is saying. By this way, sometimes, the expression here, if you see in the lecture, the expressions are so tough. How we'll get that? So now that problem is breaked in the convex type of this, using the convex property. Okay, the inner part is linear, the outer part of this is a square. So the outer part is square, which is a convex, we know, and the inner is linear, so whole thing is convex. Once we got that, okay, this is the square error. So here is a square, actually error is actually finding. And what is things, the whole machine learning problem is, we first found the error. Even if you see, even if you do the whole MLT, in MLT, I am repeating the word I have already repeated it. I said already. So in MLT, what is that? What is the algorithm, or what is a model? Model is a function, right? As we see, model is a function. You have given the data in that, you got the output something. Okay, you got the output something. You have the original function. You have the original function. What we used to do, we from the obtained one and the original one, okay, and the original one we used to subtract, we used to find the norm of it, and we'll try to minimize this error. So this is the error, right? This is the error, and we'll try to minimize it. And now this minimization become an optimization problem. Why we are learning this optimization? Because from 9 onward we have started learning optimization, where we have seen first the convex function. Why? The reason is generally square function or convex function. So let me tell you the behind the whole thing, why this is, or why you are learning only these types of function, why you are learning this all. Actually whole MLT, or even if you do the machine learning algorithms, whatever you do machine learning things, everywhere you only see the norm, okay, norm of it. A norm of what? The obtained function, where you applied your algorithm. Algorithm is any algorithm you used to see, you can see, if you do deep learning, there, the different functions are there. Okay, they used to give some different function output, they usually give get it, and now start getting that, okay, is this error is minimizing with respect to different function, or with respect to different model, with respect to other model, which one is minimizing it, and then that is going to be the best model. Even in the model section also we generally do it. And the whole MLT is that we generally find the error and minimize it. And where it's come minimization, optimization come. Now optimization we are only doing on the square. We are, if you see it, we are only doing the square error. Square error, that's what everywhere you will see the error. No different error you will see. Everywhere you will see the square error. Square function is convex function. And the inner part is, it could be linear, it could be anything. Anyhow, will to convert that problem a kind of convex function, or maybe increasing function, or maybe non decreasing function, which is increasing function. Okay. try to build like that model and easily find, okay, where it will be minima, where it will be maxima, sorry, not maxima, mostly minima. And if you see the KKT also, we are on KKT, which is, in KKT. So I will move to the KKT now. So in KKT, if we are only solving this kind of minimization effects, where your GXI, these
What
are
is
the
KK?
constraint optimization. Now you'll see these are this is the
Sir, what
subject
is
to
KKT?
this kind of problem. We generally minimize our problem. Minimize. We are studying here only the minimization problem, because our whole MLT is on the minimization. We
Full
will try
form.
to minimize our.
Full form.
Sorry, cos Karus condition is there. The cos Karus and cos Karush, cos and Karus for this one, and this T is, I'm missing the word. Oh, sorry, KKT, sorry, cos Christian.
Tucker.
Sorry.
Tucker.
And this is there are so many things our professor see here is this. So the name is, I think it is given here. Generally, the pronouns as it's different. Oh, this is the relation between the primal and dual.
What
These
it
are the
exactly means, sir?
primal and dual. I will start now the KKT. I will tell you that. Oh, he has started with the support vector. That is not even, he's just introducing it. So support vector, we'll see more and more detail in MLT only. Sorry, this is what the name is. Let me increase the quality. Cos and okay, sorry, T is for Tuketer. Okay. Cos Tuketer.
Tucker, I think.
Tucker. Okay.
No issues. Nothing.
No, it's just pronunciation. Yeah, this pronunciation is not more
Sir,
important.
name is very difficult.
Name is very difficult. Okay. So see, this KKT is now. So KKT is extensor of, you can say, the Lagrangian. Okay, the KKT is extension of Lagrangian, and this is what the very specifically we are studying here. The optimization is for the KKT only. That only we are studying minimization with this, with such constraint optimization. Even any problem, if you have, you see, any problem could be converted into in this fashion. If you have maximization problem here, okay, if you have maximization problem with this constraint on with some other constraint, you can convert. If it is a maximization, you can write the minus of fx. It will be changed to minimization. So even in starting very specifically here, but we can convert any problem. If it is even the max problem, we can convert in the minimization problem. If the constraint is given of this case, okay, we can convert with the minus g of x. Maybe there is this the same case, and proceed with the with the KKT stationary slackness. So means whenever we have some problem, we can with just sign change, we can change it to our the main in this fashion, minimization to fx with such constraints.
So did you mean to say that when we change the function to negative, the constraint also changes from less than or equal to greater than or equal to?
No, so I'm not changing the constraint. Constraint you can, so if you do so separately you can do, and changing the according to constraint is your primal to dual. That is a different. And I'm telling here is I'm just saying that if it is a problem is given in max, you can not convert. You can think in the maximization to minimization problem by this way. I'm not saying the change the primal to dual. I'm just saying you can change this signs. You can change this max min by adding the minus sign to some places. Okay, that is what I'm saying.
Sir, if
Okay.
you don't mind, can we take one question for better understanding?
Yes, yes, yes. I will do that one problem. Okay, I will do that one problem. I have, that's why I have taken one problem on here. So, so let's start now this KKT. Yeah, so I was telling about the MLT, or any machine learning. So this is why the reason is we are very specifically here we are studying on this optimization is very in a restricted area. Otherwise, optimization are very if you do the maths courses, BSc in maths, optimization you also simple like so many algorithms are there. Simplex method is there. You will see the dual, primal, dual. So many things are there. But here we are very specifically studying, even specifically or means what the extension of Lagrangian we are studying on the KKT. So here is, let me start now the KKT. So in KKT we have some problem of this function fx, and we generally see the minimization where with the some constraint would be given. Some constraint would be given such that the constraint would be till now. If you see the Lagrangian, so the constraint one. Okay, so of this case where the minimization to fx where the constraint of less than or equal to, okay, of this case. Now the thing is that if you see the lecture, professor named it. I will just name also. I will not tell you very detail. Okay, because um, even we talked with the professor, can we do some tutorial on that? They totally denied that. It is just to know that there is a primal and dual, and that's all. There would be no question to ask. Okay? And tutorial also one primal dual he did, but just for introduction. Okay, so what is a primal and dual? Is that we can think over this function with a different scenario. We can change our function to max over no, it is actually written. If you see the tutorial, it is actually changed with the different function. Here will be the different function, and the constraint it is going to be changed. And how this is going to be changed? Okay, so I will tell with the tutorial. Okay, this is called dual one. Okay, dual problem. See, previously you have the mean problem with this one, but we converted this problem to max such that with the different condition would come. Okay, so you no need to know that how it is converted. Okay, but there is a thing that we can think our problem, the original problem with this one, we can change our problem into with the different max problem. And the best thing is that when your function is when your function is a convex, then there is a thing is that strong duality holds, and the thing is that whatever this function have the optimum solution, that is called the same optimum solution is going to be held for fx, this minimization also. If your fx is convex, in that case it's going to be the strong duality hold, and whatever the minimization problem is going to be, that whatever the max problem you change the dual problem, the why we are changing it, sometime this could be difficult, okay, to solve it. So dual would be easier. Okay, this would be some easier. That is why the reason is we are changing the primal into dual. Okay, there is no other thing is that, or a mean to say why we are doing this, why we are solving this portion, because sometime this problem may be sometime tougher to solve it. Then we convert that problem into dual and we also solve it. If it is that this is also tough, or maybe more calculative or anything is there, we'll think about differently. But this primal one is maybe tougher. This is called primal. Maybe solving this is tougher, then we'll change it to dual and it may be easier. And many times, many times the dual one is not sometime, many times it will be easier. Okay. This is what the theory is. And if you want to look at that, how it is, Professor Arun is very clearly why it is so, what is happening behind it, very clearly he is explaining. Okay. So just say the few within that. If you have doubt, you can just let me know. We can discuss that. This is what the primal and dual. So the thing is that how now we solve this. So to solve this, there is a KKT condition. Ask Tucker, what is the pronunciation? Okay, whatever thing is. Okay, so this is this. It says that this very simply, as the Lagrangian function, we used to write this alpha fx2, in plus lambda times this gx. Okay, and then gradient. So here is the first condition in the KKT condition, as in the Lagrangian. We used to find the gradient. So here in KKT condition, the first one is called the stationary condition and equate to 0. By this way, we used to find the critical point. So same way, we usually find the critical point. So this is called a stationary condition. The second one is the slackness condition. The second slackness condition is lambda time. To do the lambda time here, let me write here in the same notation format how the professor is writing. So here this one, so if it is less than or equal to, so lambda time gx, this is going to be equal to 0. Okay, this is the slackness condition, and this is the primal. This is called primal condition. This is dual condition. Here it is properly written. So these all things are happening on, this professor is writing here a star. He is saying that what this is happening on the optimization. Okay, you will assume that okay, x and y is the optimum solution. You can assume, then now you can proceed. Okay, our method to solve is we generally not write there star, so we'll go with this one only. We write that and start solving that. So this is called stationary. This is called slackness. Then the third one is the dual feasibility. Just a second. Primal feasibility. The third one is primal feasibility. The second one is, the fourth one is dual feasibility. Sorry. So the third one here is the third condition is the primal dual. See, on exactly whatever the constraint is there, this is called primal dual. Okay, or whatever the exactly constraint is there, the same method, And the third one, as the fourth one is the dual optimality or feasibility. Okay, so the primal feasibility and the second the dual feasibility. Dual feasibility on the x star, sorry, lambda, on the lambda, because lambda is we are doing, no, if you lambda we are doing, this is great, should be greater or equal to 0. On the dual, once you convert this dual, this will be the max we are finding on lambda. Okay, if you see in the, that is we are finding on the lambda, so that's why here is name is dual feasibility. Okay, we are finding the dual feasibility. Feasibility, let me tell you that now the, if you we started it, so the thing is that this region, so the you have a function. Okay, the constraint optimization means here is, this is your constraint. Okay, it's a gxi, whatever the I means, you are making gx of x, gi of x less than or equal to 0. So whatever, by so many gxi is there, by that way you are finding the region. So this is your constraint region. Okay, within that region I want to find the minimum of fx. This is what the idea. Okay, this is what the idea. So the constraint region, it is also called feasible region. Okay, you can say this region, you can say this is a feasible region. Within that you want to find, so here it is also the, you can get the value of the function, here is also at the places. So this is called feasible region. So here, that's why here the dual feasibility means we are finding on the lambda. Here is in the dual you are finding the max of with respect to lambda. On the primal you are finding max of x. So that's this is why here is on x it is there. No? So this is your primal feasibility. Okay, and this is your complementary slackness, and this is your stationary. So let's do one problem. This is idea. So I want to tell you one more thing is that I don't know many of you or know it or not. Sometime your function. Let me write one function of the object. This I will tell you. I will tell you the another method also. By you no need to use this one. The question is, by question I will tell you. Let's say I have the minimization problem of this case, min of let's say x square. Even I am also giving, let's say, a convex function. Okay, where x plus y is less than or equal to 0. The second is x minus y less than or equal to, or let's say, let me change this. Let me pick a reason of it. X minus y less than or equal to, let me, here is change with the 5, and here is change with -2. I'm just randomly making it. Okay, so I will tell you with the meaning of, like, I will just tell you how we'll solve it. Let's say this is the such that this is the constraint optimization problem. Okay, so the thing is that whenever you want to solve it, you can solve by the graph. So how we can solve by the graph? The simple method is, whatever the constraint is there, I started this feasible region, that's why I started telling you. So try to draw this feasible region. Okay, how you can draw this feasible region? See, this function is a linear function, right? So if you want to draw this function is nothing else. Sorry, this represent a line. Why I'm saying the function? This is a, sorry, this is a linear equation, right? These two represent a line. So you can think this is a simply for the time being, you can do for the rough work also. This is the of this case, and this is x minus y, or even let's say x plus y is equal to -5, and x minus y is equal to 2. So you can draw these two lines. So if you draw these two lines, so both are actually, by if you draw the first line, this is going to be what? both intersecting at the below side, so means negative side. So let's say here it is, or maybe it is more here. So let's say here this is -5, this is minus. This is your line, okay? And the second one is this one. So where it will intersect, what is the line here? You can convert, no? X is equal to x is 2 plus y -2 is equal to 1. By this way, you generally used to draw it. So this is going to intersect at y at -2 and x is 2 here. So this is your second line. Okay. Now it says, oh, both are minus less than or equal to. Okay. So this, the first line is less than or equal to means below to this line. Okay. And here is also less than or equal to means below to this line. Okay. So which one is your feasible region? Lying for both is this portion, right? So the portion is this one. This is, I am just making so this is your feasible region, which lying in the intersection of both regions. So this is your feasible region. Okay. And now the case is that I made a wrong question here. So not a, means the way I want to solve, but I didn't create it in quick manner. So I mean
Here
to say there is, sorry.
here we didn't get the minimum, but
Maybe we didn't. So this is what the mistake I made it. So I mean to say I want to explain the feasible region. The thing is that where is the feasible region within that? Okay. Okay. Even this, see, this feasible region is not bounded also. Okay. This is not bounded. But our problem, our course is done for the bounded one. Okay. This is not the case. So this is not bounded, not bounded feasible region. The case is that to solve your region should be feasible and bounded. So even if I should to add x then greater than 0, y greater than 0, these all conditions are needed here. So you will get a bounded feasible region like this. Okay. Maybe I'm saying, maybe this is what
we
you
have
bound.
we have a question on KKT.
I have question. I have been that is not in in the visualization, in visualization form. I will tell you, visualization you can do with the two variables. If you have it is on three variable, then it would be difficult. Okay.
Okay.
So I am just telling. So suppose you draw the feasible region and like this you got. So you got the corner points here, here, and here, and where it will give the minimum value, you can substitute. That is you're going to be the minimum, because the minimum is going to be the optimum solution is going to be on the corners. So by this way, you can just substitute where it have minimum. You can get that this is a minimum. So I made this is a not whatever this constraint I given, that is not a proper constraint. Otherwise, by if I to choose this question from some book, then it will give a proper feasible region, bounded feasible region. And if you solve it, you just need to take the corner points and substitute in the objective function where it is minimum. That is you're going to be the optimum solution. This is a simple method sometime you can use to solve in the two variable cases. No need to go with the KKT, right? This stationary condition, complementary slackness, primal dual. These are not needed. Okay.
Also Lagrangian.
Also, so even that is what the KKT extension of. So let's do one problem on it. Okay, I have one problem. So let's do one problem. So yeah, I think this is in two variable only. Okay, I will verify also. So this is good. I didn't check it. Let's do this problem. I will solve with the both method. So this is the minimization problem subject to some constraint is given. So all of you try it. Let's see what is going to be. So all of you solve with the KKT. Okay. I will solve with the whatever I just discussed the method, and let's see who is getting matching with the correct option. Okay. So please try first, and then I will solve with the whatever I just now discussed the method. I think it is in the tutorial it is discussed. So who have doubt? No, any specific doubt? Please let me know. Okay. Any general doubt we have? Anyone reaches to the answer very fast? Even the third, fourth is, it is nothing but you can not use it. It is nothing but your, less than or equal to. It means if you just multiply this saying that fourth variable should be positive. This is a general case. If you found it somewhere, this all things are given. So we generally not use it. So this is nothing but your Lagrangian problem. But yeah, less than is there. So you can solve with the KKT.
Answer is 4.
4. I'm not sure. Let's see it. So everyone, please see it here that I'm solving with first whatever I had just discussed with the graphical method, because this is given in two variables. So let's solve by that way. Then I will proceed with the KKT. So see this. This is the constraint one. Okay. So let's find. So not only this one. This all actually constraint. So let's draw the feasible region. So if you draw it here, so you can write this as a x plus y equal to 2, right? So that means this is the line. And now x is greater than 0, y is greater than 0. So this is what it is. So no, so you said no, I think you said maximum. No, I think you said maximum value. It is for minimum. Okay. So see this is the feasible region now. X is greater than 0, y is greater than 0, and below to the line. So below to the line, this is your line. X plus y is equal to 2. So, and this is less than or equal to is there. So below to the line. So this is your feasible region. Okay. Now I said no, on the corners, it have the optimum solution. So on the corner, this is, this point is your 2, 2. And this point is also, sorry, not this is 2 2, this is 0 2, sorry, and this is 2 0, and this point is your 0 0. Now substitute one by one. So add 2 0 0 2, it is going to be 4. So add 0 2. Add 2 0 is also going to be 4. Right? You just need to substitute. And at 0, it is going to be 0. I want the minimum one. So the minimum is of the function is 0 within the constraint. I think you set the maximum one. I ask for the minimize. This is the minimization problem. So by graphical, it will be simpler. No, very simple. You can do without this one, and you can get easily the answer. But sometimes, question would be given in the KKT way method also. Okay, you see the older question paper. There, some question would be given in the in the KKT method. Maybe Lagrangian function would be given. Some KKT condition would be given. Within that, you have to choose the correct option. So you have to follow the KKT steps. So KKT says that first find the Lagrangian. So Lagrangian is this is. So I will not use this too. Okay, there is no use of it. Okay? Because it would be given in anyhow in the question. So let's use only the second and the first constraint. So gx plus lambda time g1x. And now this is the Lagrangian function. I have to get it, the gradient of it. So this is gradient of fx plus lambda time gradient of gx, g1x, and this is equal to 0. So if you do it, this is going to be 2x 2y, right, plus lambda time g1x. So g1 is this one. If you do find the gradient is what? What is gradient here? G1 of G1? Anyone? No? 1 1 only, right? If you have difficulty, I will let me write here. I have this. The first is fx. Okay, f of xy. So x square plus y. So gradient of it is nothing but your partial derivative of f with respect to x and the partial derivative with respect to y of f. This gradient function is a vector valued function. So it's a vector. So here it is. This is going to be, if you derivate f with respect to x, okay, derivate the full f with respect to x. You can treat the first one as a variable with for the where is the x is there. You can treat as a function of x, and the second y variable as a constant. You can treat that, and this is going to be 2x. So this is going to, if you're treating this function as a variable of x, sorry, variable of x, so y as a constant, and this will be easier. This will be 0. Okay, and now by this way, the 2x will get. Similarly for the y, so 2y will get. Okay. And here is also the same way. So g1x is x plus y minus 2 is there. So with respect to partial derivative of g with respect to x is going to be 1 here separately, and for g is with respect to y is 1. The constant one already will be a 0. So this is what you will get the gradient. Now you got this, so this is going to be 2x plus lambda is equal to 0 and 2y plus lambda is equal to 0. And now this is your stationary condition. Okay, by this way you got one equation. Now you use the slackness. The slackness is complementary slackness. So lambda time g of g1 of x is equal to 0. So if you multiply it here, lambda time this 2x, sorry, x is there only, x plus y minus 2. Okay, this is equal to 0. So it says that either this is going to be 0 or this is going to be 0. Okay, So if you take lambda is equal to 0, so in this case, so see this complementary slackness says this is what we got, and the third one is okay. So this is what we got, and the third one is the primal feasibility. The lambda, sorry, primal feasibility says what, the whatever the G1x is equal to 0, okay, and the dual feasibility says lambda is equal to 0. This is what, right? One by one the KKT conditions, right? This is what, sorry, less than or equal to 0, and this is dual feasibility is greater than 0. This is why, the reason is because increasing. So that's what this is, less than or equal to 0. Okay. So even these are not needed. Even these are enough to solve it. Okay, using this one, or you can solve it. So here from it, even this, see, these are all needed to find a proper equation to solve it. So this all condition is anyhow. If you have more constraint is there, you will get more. So you needed more equation. No, if you have more constraint, or mean to say, if you have more variable, okay, if you have more variable x, y, z, lambda, mu, omega, if more such kind of parameters or variables are there, you needed more equation, then you can easily solve it. That's why this complementary slackness, dual feasibility, primal feasibility, or from the stationary also you are getting the equations. So this, we have, once we have more variables, we needed more equation to solve it. So from here, this is what the dual feasibility is there. The primal feasibility is less than or equal to, okay. So from here, either could be lambda is 0 or this part is 0. So if we choose lambda is equal to 0, these equations will give what, x is equal to 0 and y is equal to 0. So even we don't need this, the second condition. If you check it, if x is equal to 0, y is equal to 0, and see our function is x square plus y square. Okay. So I'm now, see, use your, use your whatever you know, the tricks. Once we got, okay, the possible value of this is true, right? For lambda is also following the condition. This is greater or equal to we need, because our constraint is less than 0. So this is following the condition of dual feasibility. So totally fine it is. We are within the feasible region, and we got the value of x and y, which is 0, 0. Our function is a complex function. Okay, so it have sorry, so convex function. See, this is a positive also. This is always going to be positive value. And once we substituted 0, 0, we are getting 0 value. And this function is minimum value. And see what, this is a positive function, and we got the minimum value as 0. Will that be any other value which is less than that 0, and our function is always positive? No, right? So by this way, no need to further to take this x minus y condition, this condition, and assuming to 0 to solve those all. No needed. Once we are got this, okay, lambda is 0, and by that way we got x is equal to 0, y is equal to 0. Use the method of the convex, okay, or either the different way you can say this, our function is a positive function. So positive function means the minimum value of the positive function is 0. So by that way, the minimum of this function is just, you can say, 0. So you can use the tricks also while solving. No need to, even sometimes no need to follow the whole condition. Need is that you are doing, this is objective course you are doing, not a subjective. So you can use the trick very fast. Okay. So by both method, by graphical method and by this KKT, we solve the problem. Okay. See, this is I use this solutions by very, this is given the chat GPT. I don't want to see this. no need to use this bigger. By the simple argument, you can argue that, okay, if I assume one condition only, lambda is greater or equal to 0, or we found that lambda is 0, apply on that to find the value of x and y. Once we found x and y, we got, okay, it has the 0 only. 0 value also we have on this function. The minimum of this function is have 0 also. With this, it is following on the within the feasible region. So no value is going to be lesser than 0 for this function. It cannot attain minus value. So the minimum of this is 0. You can directly take. Okay? By argument, you can give the answer. Otherwise, you can follow the whole condition. Okay, let's solve for now that this condition. You can solve still whatever the answer you will get for x is equal to 0, y is equal to 0. So once you proceed by this method, no, you will get the critical points also. What the critical points? 0, 2 and 2, 0. As here I solve by this bounded. So if you assume to be lambda is 0, you got x is equal to 0, y is equal to 0. If you proceed by this method, you will get 0, 2 critical point means x is equal to 0, y is equal to 2. Okay, this will be x and this will be y, or 2 and 0. This will be x and this is y. So three critical points will get 0, 0, 0, 2 and 2, 0. And now you will start substituting which one is giving minimum. That is your optimum solution. But I didn't go, I did just directly jump to the condition that, okay, our function is positive function, it have never negative value, and we got the 0. So minimum is going to be 0. So no need to, very quickly you can jump to, you can skip this part. Otherwise, if you want to go, you can solve it if it is a subjective paper. Okay. So is this understandable? Is this clear bit? Sometimes you need to use the tricks also. Is this clear? No, not clear. Okay. So I will suggest you to sometimes, this is a quick idea. Okay. Sometimes if you are looking at your problem is in two variable, your function is given or subjective constraint two variable. Just try to solve by the graphical method. It will be very easy. Just try to correctly draw the feasible region, found the corner points, substitute in the function, which one is giving minimum. You can directly answer that, okay, the minimum value of the function or optimum value of this optimization problem is that one. So graphical is very easy sometimes if your problem is given in the two variable. If it is in three variable, then no method will work. Only you have to follow the KKT. Then you can solve. In KKT also, while solving KKT, use the trick. You see the method. Okay, is there anything I can reduce my work? As just now I did one trick. And I have given to solve that in ChatGPT. He solved very long method. I see that, oh, very dangerously. He's solving one by one. You can follow that. Okay. Clear? Any doubt? Any other doubt? So this is what in week 10 we'll see in Solvitas also with some problems. Anyone to say something or having doubt can ask. Okay. All of you very silent. I don't know how I'm teaching. Is this understandable or not? Is this fine, right? To all of you able to understand?
Yes, sir. Yes, sir.
Yes, sir.
Okay. Thanks, everyone. Thanks for joining. I'm now stopping the session. If you have doubt, please let me know. I will discuss it. I'm here. Otherwise, we'll wrap up the session. Okay.
Thank you, sir.
Yeah. Thanks. Thanks, everyone. We'll see you on Saturday.
Thank you, sir.